Bring a massive 6-foot glass box into a residential space, and you immediately introduce a complex engineering problem. This wireframe shows a 125-gallon aquarium. At 72 inches long, 18 wide, and 22 tall, it occupies a massive floor block. Fill it with heavy glass, 2 to 3 inches of sand substrate, and water. The combined mass climbs past 1,400 pounds. That concentrated weight is heavy enough to stress standard residential floor joists. Safely supporting this mass often requires placing the stand directly over load-bearing walls or consulting a structural engineer before filling it. If a giant tank requires a reinforced stand and hundreds of dollars in heavy-duty equipment, the logical alternative seems obvious. Start with a simple, lightweight 20-gallon tank. Beginners usually assume a smaller volume means less work and lower risk. For keeping aquatic life alive, the exact opposite is true. To understand why, we have to shift our perspective from the physical room down into the microscopic environment of a beginner tank. This models a standard 20-gallon enclosure. Watch what happens when a single decaying leaf drops into the closed system. The line graph spikes sharply upward. That decaying matter breaks down into toxic ammonia. With so little water, the concentration rapidly reaches lethal levels. This low water volume also lacks the mass to resist environmental shifts. A slight draft from a window or a brief heater malfunction can cause severe fluctuations in temperature and pH within hours. Maintaining a low-volume aquarium means constantly fighting against the physics of a fragile, rapidly collapsing environment. Every minor mistake is amplified. Expand the physical volume of the water, and the chemical rules governing the environment shift in your favor. This side-by-side chart compares that fragile 20-gallon setup directly against the massive 125-gallon system. When we drop that exact same unit of waste into the larger volume, it dilutes instantly. The water chemistry barely registers a shift. The engine keeping this water safe is the nitrogen cycle. A tank of this size provides a massive surface area inside the filters and substrate for beneficial bacteria to colonize and thrive. This flowchart maps the biological process. The bacteria consume toxic ammonia, convert it into nitrites, and a second colony eventually breaks those down into safe nitrates. Cultivating this cycle takes a stable 4 to 6 weeks. This buffering effect also applies to temperature. If a heater temporarily fails, 1,400 pounds of water cools down incredibly slowly, protecting the fish from thermal shock. The heavy physical burden of the tank provides an impenetrable biological shock absorber. The sheer mass of the water does the hardest work for you. When you establish that stable, heavy ecosystem, the visible payoff is striking. The true value lies in its specific geometry. While total volume provides chemical stability, the 72-inch horizontal length acts as a crucial swimming runway. This top-down scale blueprint compares the spatial limits of these tanks. Territorial giants, like adult oscarfish that grow up to 14 inches long, require this expansive 72-inch boundary simply to move naturally and establish territory. That 6-foot span also accommodates the behavioral needs of hyperactive schooling species, like rainbow fish. They require long, uninterrupted sprint distances to burn energy and thrive without chronic stress. Accepting the heavy engineering requirements of a 1,400-pound setup and patiently waiting through the 6-week microscopic cycle buys you permanent biological stability. You secure the awe-inspiring beauty of a giant aquatic ecosystem by respecting the uncompromising physical science of its scale.